Welcome to the Deep Dive, where we plunge into the heart of what's shaping our world, giving you the shortcut to being truly well-informed.
Great to be here.
Today we're talking about something that honestly felt almost futuristic just a few years back. Something that's really rapidly transforming the very fabric of our digital existence.
It really is. The pace is incredible.
Yeah, think about it. Not long ago, coding was often seen as this highly specialized, almost mystical art.
Right, reserves for a select few. People thought you needed some kind of special brain for it.
Exactly. But now there's this profound transformation happening, reshaping everything we know about creating software, opening it up. It feels like a whole new era.
That's a fundamental shift, definitely. And it stretches far beyond just the tech industry itself.
How so?
Well, it's redefining not just how we interact with technology day to day, but also our own creative potential. In a world that's increasingly built on code, this changes who gets to build it.
Absolutely.
Yeah.
It's like pulling back the curtain on something that might seem abstract, maybe a bit technical, but is profoundly impacting our future.
Couldn't agree more.
So today, we're taking that deep dive. We'll look into the very essence of software, starting with the foundational languages that build our digital world.
The building blocks.
Yep. And then we're propelling ourselves into what feels like a revolutionary new era. Software 3.0, powered by this fascinating concept called vibe coding.
Sounds exciting.
It is. Our mission here is, as always, to cut through the complexity. We want to extract the most important nuggets of knowledge, the key insights from our sources.
Give you that shortcut to being really informed.
Exactly. Get ready for some serious aha moments because we're about to unpack some truly, truly interesting developments.
Okay, let's get right into it then. Before we jump into the cutting edge, the really new stuff, it's probably crucial to lay the groundwork.
Good idea. Back to basics for a second.
Just to make sure we're all on the same page. What is software, really? At its absolute core, software is just a set of instructions.
Instructions. Okay.
Yeah, instructions, data, or programs that enable hardware, your computer, your phone, even your smart fridge, to execute specific tasks.
So it's the brain telling the physical stuff what to do.
Precisely. It's the brain that brings the physical components to life. Unlike hardware, which you can touch, it's tangible.
Right.
Software exists as abstract code. It directs operations, it processes data, provides services to users, to other systems. It's the dynamic part, the changeable part.
The invisible force making almost everything run these days. And I've always been a bit curious about the term software engineering.
Yes.
Why not just software development or, software art? Does engineering imply a kind of rigidity, maybe, a formal process that clashes with how fast things move now?
That's a really thoughtful question. And the engineering aspect is actually key to understanding the rigor involved.
Okay.
It signifies that creating software isn't just artistic expression or simply banging out code. It's meant to be a rigorous application of scientific and mathematical principles.
So more structured.
Exactly. We're talking about structured processes, mathematical rigor, scientific methodologies. Think about the software development life cycle, the SDLC.
Right, the whole cycle.
From requirements gathering, design, coding, testing, deployment, and then maintenance. That whole life cycle highlights why it's a domain needing precision, systematic approaches, a robust framework.
Like building a bridge, you need a plan.
Very much so. It's like building a bridge or a skyscraper. You need careful planning, execution, testing. It's about building reliable, scalable systems, and that often demands that level of formality, that engineering discipline.
That makes a lot of sense.
Okay.
We interact with so many different types of software every single day, often without even realizing the distinct roles they play.
Absolutely. We swim in it.
Can you give us a quick run through of this diverse landscape? Because it's definitely more than just the apps on your phone, right?
Yeah. Oh, much more. Think about it in layers, each performing a specialized function, all working together to create the digital experience you actually perceive.
Layers. Okay.
Starting at the bottom, maybe. The unsung heroes, the foundational pieces, system software.
The fundamentals?
Right. These are the basic managers of your hardware. They act as the bridge between the raw silicon, the chips, and the programs you actually use.
So the operating system.
Exactly. Operating systems are prime examples. Windows, which, almost every desktop or laptop has. Linux, which is huge, powering the vast majority of servers and production environments. It really underpins the internet itself.
And Mac OS for Apple users.
And OS, of course. Without an OS, your computer is just, Well, a box of inert parts.
A paperweight.
Pretty much. This category also includes device drivers, those little bits of software that let your hardware like printers, graphics cards, webcams talk to the operating system.
Ah, okay, the translators.
Kind of, yeah. And utility programs, too. Things like disk management tools, antivirus software, backup utilities. They help maintain and optimize the system. They manage the core stuff.
Got it. So that's the base layer. What's next?
Next up, you have application software. These are your direct tools, the programs you actually interact with to get specific tasks done.
Like Word or Chrome or...
Precisely. Everyday examples, Microsoft Word, Google Docs, web browsers, all those mobile apps on your phone for social media, navigation, games, whatever.
On bigger stuff, too.
Oh, yeah. On an enterprise scale, you have ERP systems, enterprise resource planning. They integrate core business processes like finance, HR, supply chain, and CRM systems, customer relationship management for managing customer interactions.
So purpose-driven software. A browser gets you online. Excel crunches numbers.
Exactly. Each designed for a specific purpose. Now, between these two layers, there's often something called middleware.
Middleware. That sounds a little...
It is. It's fascinating because it's software designed specifically to connect other software components or applications. It lets them communicate and exchange data.
So you don't directly use it, but it's working behind the scenes.
Correct. You don't usually interact with it directly, but it's vital for complex systems. Think of different kinds of databases, relational ones like MySQL or PostgreSQL, NoSQL ones like MongoDB,
Okay.
or message-oriented middleware that lets different systems talk to each other asynchronously. Web servers like Apache or Nginx, application servers like Tomcat, file servers, document servers, image servers.
Wow, okay. Lots of connecting pieces.
They're the invisible links, the plumbing layer, if you will, allowing all these disparate systems to work together seamlessly.
Okay, that clarifies the layers. Any other big categories?
Yeah, there's a broader group of specialized software categories. This includes things like diagnostics and utility tools for troubleshooting, embedded software, that's the firmware inside your smart appliances, IoT devices, the real-time control systems in cars or industrial machines.
Firmware.
Mm-hmm.
That's low-level stuff, right?
Very low level. Firmware is specifically the code providing essential instructions for hardware initialization and basic control when a device first boots up. And then there's network software.
Like managing networks.
Yes, and a huge modern trend here, especially with the cloud, is infrastructure as code, or IAC.
IEC, I've heard that buzzword.
It's more than a buzzword now. It's where you provision and manage your IT infrastructure, servers, networks, databases, everything, not by clicking buttons or plugging cables, but using code.
So you write code to build your servers.
Essentially, yes. It brings the precision, version control, and automation benefits of software development to infrastructure management. It's massive in cloud environments.
So it really is this beautifully complex, multi-layered cake, isn't it?
That's a good way to put it.
Application software sits on system software, which relies on the OS, which talks to the hardware.
Yeah.
And thinking about AI, this is mind-bending. AI isn't just writing code for one layer.
No, not at all.
It's learning to navigate and generate code across this entire stack. It feels like it's fundamentally changing how we design systems, from the top app all the way down to provisioning infrastructure with IAC.
Precisely. It's a holistic transformation we're witnessing. And that brings us beautifully to the next crucial layer, the actual language these systems speak.
The programming languages.
And crucially, how that conversation itself is rapidly evolving.
This is where it gets truly fascinating for me. Programming languages, the very fabric of all this software we've been talking about.
The DNA of the digital world.
Yeah. And when we delve into them, it helps maybe to draw an analogy to human language, right?
It's a useful analogy.
Just like we use English or Tamil or Chinese, each with its own vocabulary, its syntax, its grammar, its semantics. Programming languages are standardized sets of instructions for computers.
Rules for talking to the machine.
Right. Historically, humans painstakingly created this code, line by line, defining all the logic in source code so computers could understand and execute it.
A very manual, detailed process.
But what's mind-boggling now, and this is where we're heading, is this new trend of vibe programming and AI-assisted or even fully AI-generated software.
Mm-hmm.
It hints at a future where computers play a much larger, maybe even autonomous role in creating the code itself.
It completely changes the dynamic. The nature of the conversation between human and machine is shifting under our feet.
That's the inflection point we seem to be racing towards. But first, let's unpack how these languages have traditionally worked. How do we classify them? It's not just one big bucket, is it?
Not at all. There are several useful ways to categorize them. One key way is by their level of abstraction.
Abstraction, meaning how close they are to the machine versus how close to human thought.
Exactly that. How much detail of the underlying hardware is hidden from the programmer.
Okay, so what are the levels?
At the very bottom, you have machine languages. This is the lowest level, the most fundamental. It's the raw binary, the zeros and ones that the CPU understands directly.
The native tongue of the processor.
Precisely. Writing in machine code is incredibly difficult, tedious, and error-prone for humans. Imagine trying to write an essay using only 2 symbols.
Yeah, no thanks.
Then, a step above that came assembly languages. These use mnemonic symbolic codes like ADD for addition, or MOV for moving data as a representation for machine instructions.
A bit easier than ones and zero.
A bit, but still very low level, very tied to the specific processor architecture. You need a deep understanding of the computer's internals, often used for performance-critical stuff or directly manipulating hardware where every clock cycle counts.
Right, still pretty hardcore.
Definitely. The real leap for human readability and widespread adoption came with higher-level languages.
This is where most developers live, right?
Yeah.
C++, and Python, Java.
Exactly. These languages use syntax much closer to natural human language, often English-based. This makes them significantly easier for developers to write, read, debug, and understand.
So you focus more on the problem, less on the machine details.
That's the goal. C++, Python, Java, C#, JavaScript. They allow developers to think at a higher level of abstraction. The key takeaway isn't memorizing dates or syntax details for all of them,
Right.
but to see this relentless march towards more human-readable, more powerful abstraction, making programming accessible to more people over time.
Okay, so from cryptic machine code towards something more like human language. But it's not just about how high level they are, is it? There's also the paradigm,
Ah, yes, the programming paradigm.
which sounds like the fundamental philosophy.
Yeah,
The way developers are taught to think about solving problems with code.
that's a great way to put it. It's the core intellectual framework. How do we structure our thoughts when instructing a computer? Because how we think about solving problems directly influences the structure, the maintainability, the capabilities of the software we create.
So different schools of thought for writing code.
Exactly. And these different philosophies lead to significant differences in how software is constructed, affecting everything from how easy it is to update to how well it scales.
Okay, what are the main paradigms then?
Well, one of the earliest and still relevant ones is procedural languages, or POP, procedure-oriented programming.
Procedural, like following steps.
Precisely. The core idea is a linear flow, step-by-step instructions. Programs are organized around procedures or functions that operate on data.
Okay.
Communication usually happens by passing data between these procedures. Importantly, data and the functions that operate on it are often separate.
Separate, how does that work?
It means you might have data defined globally or passed around, and different procedures can access and modify that data. This can sometimes lead to issues, as there's often limited inherent security at the programming level controlling who can change what data.
Ah, okay. Less control over the data itself. What are some examples?
Classic examples include C, Pascal, BASIC, and COBOL. Historically, they were incredibly important, great for system programming, mathematical stuff, early business apps because they were efficient and gave direct control.
C is procedural then. Got it. What came next?
A major paradigm shift was object-oriented programming, or OOP.
OOP. Heard that one a lot. What's the core idea?
It moved away from just sequential procedures. Instead, OOP tries to model real-world entities as objects right there in the code.
Objects, like a customer or a car or an order.
Exactly. Each object has 2 key things. State, which is its data or properties, like the color of a car or a user's name.
Okay.
And behavior, its functions or methods, the things it can do, like a car accelerating or a user logging in.
State and behavior. Got it.
And the absolute key here is that the data, state, and the functions that operate on that specific data behavior are bundled together within the object. This is called encapsulation.
Bundled together. So the object holds its own data and the ways to change it.
Yes. And this allows for something called data hiding through access modifiers you might have heard of, private protected, public.
Oh, yeah.
It means the object itself controls what information it exposes to the outside world and what operations can be performed on its internal data.
So it's like the object decides what to share. You wouldn't tell a stranger the same things you tell a close friend, right? It creates a kind of self-contained unit.
That's a perfect analogy. The object maintains its own internal integrity. It protects its state.
That sounds much more organized, especially for complex systems.
It really is. And some languages, like C++A, even have this fascinating concept called friend functions.
Functions.
Yeah, these are functions that are not part of the object itself, but are granted special permission to access its private or protected data. They can explicitly break encapsulation.
Why would you want to do that?
It simulates that real-world idea you mentioned. Sometimes you need to share sensitive internal information with a trusted friend. Another specific function or class, even if you wouldn't share it more broadly, it's a very specific, controlled way to allow necessary interaction without opening everything up. It shows how deeply these paradigms can reflect real-world relationships.
Wow, that's quite philosophical for code. So what does this all mean beyond just writing code? You mentioned OOP connects to the bigger picture, especially with AI. It feels foundational.
It really is. What's truly fascinating and maybe a bit mind-blowing is that these OOP principles, designed decades ago, are now fundamental concepts for many cutting-edge AI ideas.
How so?
Well, think about that core idea. An object with encapsulated state and behavior. That's not just a programming trick anymore. It's essentially the philosophical blueprint for how we're now conceiving intelligent AI agents.
Agents, like autonomous AI entities.
Exactly. Agents that can perceive, reason, act, learn, and make decisions autonomously. The OOP object model provides the conceptual starting point.
Okay, I see the link. What else?
Think about ontological modeling in AI. That's where you structure knowledge about the world by defining entities, their properties, and their relationships. Very object-oriented thinking. Or digital twins.
Digital replicas of real things.
Yes. Digital replicas of physical objects, or even entire systems that maintain their state and simulate their behavior in real time. Again, built on that object concept. These ideas, central to advanced AI and this whole emerging Software 3.0, were philosophically enabled by OOP thinking at the language level.
So languages like C++, BRICE, Java, Python, C#, their dominance makes sense because they support this way of thinking.
Absolutely. They allow for highly...
A rich tapestry indeed. Okay, another way to classify them is how the code actually runs.
Right, the execution model. This often dictates performance, portability, and even the development workflow.
Okay, what are the more ways?
There are three main models. First, compiled languages.
Compiled, like C or C++N.
Exactly. Here, the entire source code you write is translated into machine code, those zeros and ones, before you run the program. This translation is done by a special program called a compiler.
And it creates an executable file, like a .exe on Windows.
Yep. The big advantage here is speed. Because the code is already translated into the machine's native language, it executes much, much faster.
Makes sense. Any other benefits?
Yes. A significant one is left-shifted testing. The compiler checks your code for syntax errors and many types of logical errors before you even run it. It catches problems early.
Preventing runtime surprises, what's the downside?
Usually less portability. Compilers are often specific to the operating system and hardware architecture. So code compiled on Windows might not run on Linux without recompiling. And the development cycle can feel a bit longer because you have that distinct compilation step.
Okay, so C, C++S, also Rust, Go. Often used for performance-critical stuff.
Exactly. Operating systems, game engines, high-frequency trading systems, scientific simulations, where speed and efficiency are paramount.
Got it. What's the opposite of compiled?
That would be interpreted languages.
Like Python or JavaScript.
Perfect examples. With interpreted languages, the code is not precompiled into machine code. Instead, it's executed line by line at runtime by another program called an interpreter.
Line by line, so it translates as it goes.
Correct. The big advantage here is a much faster development cycle. You can write some code, run it immediately, see the results, debug, edit, run again, very quick iteration.
And portability.
Highly portable. As long as the target machine has the right interpreter installed, the same code can run on Windows, Mac, Linux, etc. The interpreter handles the OS-specific translation on the fly.
So faster development, more portable. What's the catch?
The catch is usually slower execution speed. Because that translation is happening constantly during runtime, it adds overhead compared to precompiled code. Also, errors might only be detected when the program actually hits that specific line of code during execution, which could be much later.
Okay. Python, PHP, JavaScript, shell script, great for web apps, scripting, Data analysis where maybe raw speed isn't the only priority.
Exactly, where development speed and flexibility are often more important. Now, there's a third category that tries to bridge the gap.
A hybrid.
Kind of. These are often called just-in-time, JIT, compiled languages, or bytecode languages. Java and C# are the most famous examples.
How do they work?
It's a two-step process. First, your source code is compiled, but not into native machine code. It's compiled into an intermediate machine-independent format called bytecode.
Bytecode. Okay. Not machine code, but something else.
Right. Then, this bytecode is executed by a virtual machine, VM, like Java's JVM or .NET CLR. Now, here's the clever part. The VM interprets the bytecode, but it also often includes a just-in-time JIT compiler.
Just in time.
Which means, as the program runs, the JIT compiler identifies frequently executed sections of bytecode and compiles those specific sections into native machine code on the fly, optimizing them for the current hardware.
Ah, so it compiles the hotspots during runtime.
Precisely. This gives you the best of both worlds, in theory. You get the portability of interpreted languages, because the bytecode can run on any VM, combined with performance that gets close to fully compiled languages for the parts of the code that run often.
That's why Java had that "write once, run anywhere" slogan.
That was the whole philosophy,
Right.
enabled by the JVM and bytecode. Java and C# are huge in large-scale enterprise applications because of this balance of portability, performance, and their extensive libraries and tooling.
That's a really clever compromise. Okay, so we have levels of abstraction, paradigms, execution models. Yeah. And languages also evolved over time, right? Generations.
Absolutely. There's a clear historical progression, generally moving towards greater abstraction and making things easier for humans.
Can you walk us through that briefly?
Yeah.
The generations.
Sure. It really starts in the 1940s with first-generation languages, 1GL. That's just raw machine code. The zeros and ones.
The absolute beginning.
Then second-generation languages, 2GL, in the 50s and 60s. That was assembly language, using those mnemonics, a small step up.
Okay.
The big leap came with third-generation languages, 3GL, starting in the 1960s. These were the first truly higher-level languages, often procedural or later object-oriented. Think Fortran for science, COBOL for business, and crucially, C.
C comes up again, such a foundational language.
Absolutely pivotal. C struck this amazing balance. It allowed high-level application programming, but also low-level system programming, letting you talk directly and efficiently to the operating system, to the hardware. It was incredibly powerful.
And then C++ built on that.
Right. C++ took C and added object-oriented capabilities, bringing OOP into the mainstream in a very powerful way. It let us model reality, complex systems, in this new, modular, object-based fashion.
And then there's Python. You mentioned its longevity.
Python is a fascinating case. It started relatively early, but has just grown and grown in popularity. Today, it's arguably one of the most dominant languages.
Why is that?
It's incredibly versatile. You can use it for web development, system scripting, data science, AI, machine learning. And crucially, it has this enormous, thriving ecosystem of libraries and frameworks for almost anything you can imagine. It's been a giant for 20, 30 years, and its demand is still increasing, especially because of AML.
The Swiss Army knife, truly. Okay, after 3GL.
We saw fourth-generation languages, 4GL, emerge in the 70s. These were often even more abstract, more domain-specific, focused on what you wanted to achieve rather than how. SQL for databases is a classic 4GL, MATLAB for math and data analysis.
So letting non-programmers do more specific tasks.
That was often the goal. And finally, fifth-generation languages, 5GL, from the 80s. These focused on logic programming and constraint satisfaction, like Prolog. You tell the computer the constraints and the goal, and it tries to figure out the solution. While maybe less mainstream for general programming, their ideas about declarative programming and reasoning are actually very relevant again now with AI.
That whole journey,
Mm-hmm.
it's about making it easier for humans to tell computers what to do, step by step, generation by generation.
Exactly. More abstraction, more power, less low-level detail to manage.
But traditionally, mastering any of these, especially 3GLs like C++ or Java, meant a huge learning curve, right? Years of specialized expertise.
Definitely. Developers need a deep understanding of syntax, libraries, best practices, algorithms. It was, and still is, a significant intellectual investment.
But here's where it gets really interesting again, connecting back to AI. You're saying that dependency on mastering syntax is shifting.
Dramatically shifting. Thanks to the incredible advances in AI, especially in natural language processing, NLP, and these powerful new agentic AIs, Machines can now generate significant amounts of code themselves.
Generating code. So the AI writes the Python or the Java.
Yes, it fundamentally eases the burden on the human developer of remembering every last syntactic detail or complex logic pattern. The machine handles more of that grunt work.
So this is where prompt engineering comes in, this new art form.
Precisely. It's becoming the new way of programming in many contexts. You're not writing lines of C++ anymore. You're writing natural language prompts, instructions in English or another human language to an AI system.
And the prompt is the program, essentially.
In many ways, yes. Prompt program is the emerging concept. You communicate your requirements, your desired outcome, maybe provide some examples, and the AI generates the actual source code. Could be 3GL code, like Python, JavaScript, C++, or even higher level constructs.
Wow. So the skill shifts from knowing syntax to knowing how to ask the AI correctly, how to give it the right context.
Exactly. It moves the developer's focus up a level. From meticulously crafting low-level syntax to the art and science of crafting precise, unambiguous, context-rich prompts to guide the AI effectively, it's about collaborating with an increasingly intelligent machine partner.
This must radically change how architects and developers even choose which language to use for a project.
It does. It's less about which language do I know best, and more about which language is best suited for the task, considering the AI can help generate it. The strategic thinking changes.
So the choice is still important, but maybe for different reasons, based on trade-offs.
Absolutely. The decision-making process becomes much more about the holistic system design and the inherent characteristics of the language itself. You're weighing complex trade-offs. Things like performance needs raw speed versus maybe memory safety guarantees, flexibility versus having a more rigid structure, the maturity and size of the ecosystem, the libraries, the community support, how well it handles concurrency for multi-threaded applications. And still, yes, the availability of human talent who can oversee and refine the AI's output for that language.
Can you give some concrete examples? Where would you still pick certain languages?
Sure. For, say, high-performance computing or game engines, you'd likely still lean towards C++ for that fine-grained control and optimization. Maybe Fortran for its incredibly mature scientific libraries. But Rust is gaining huge traction here, too.
Why Rust?
Because it offers C++-like performance, but with strong compile time guarantees about memory safety, eliminating whole classes of common nasty bugs. Julia is also interesting high-level, easy syntax, but often achieves C-like speed.
Okay. What about systems where safety is absolutely critical, like airplanes or medical devices?
For safety-critical systems, you'd look at languages like Ada, which was designed for this, Rust again because of its safety features, maybe even languages like Idris that allow for formal mathematical proof of correctness, minimizing bugs to an almost theoretical degree. Reliability is non-negotiable there.
Makes sense.
Both.
What about the web, the back end?
For the web backend, Go is really popular for its built-in concurrency support, great for microservices. Java, C#, Kotlin remain enterprise workhorses, robust, scalable. Python and Ruby are often chosen for developer productivity, getting things built fast, especially in startups.
And the front end, what the user sees.
Web frontend is still overwhelmingly JavaScript territory, running natively in the browser, but TypeScript is huge now.
Why TypeScript?
It adds static typing on top of JavaScript, catches errors early, makes large code bases much more maintainable. Then you have frameworks like React, Angular, Vue, all built on JSTS, powering modern interactive experiences. Elm is another interesting one, focused on reliability.
And the big one, data science and machine learning.
Data science ML. Here, Python is the undisputed king.
Why so dominant?
The ecosystem. Libraries like NumPy for numerical stuff, Pandas for data manipulation, scikit-learn for traditional ML, and then TensorFlow and PyTorch for deep learning. It's just vast and incredibly powerful. R is also strong, especially in statistical research and visualization. And Julia is gaining ground as a potential high-performance alternative.
Okay, and just for quick scripts for prototypes?
For rapid prototyping or scripting, Python again is fantastic. Ruby too. Perl is still great for text manipulation. Groovy is another option, languages where you can get something working very quickly.
So it really isn't about one language ruling them all anymore. It sounds like engineers need to be adaptable, maybe understand several languages, be polyglot.
That's increasingly the reality. Polyglot programming. You need adaptable engineers who can understand the concepts and leverage the right tool for the job, often integrating systems built in different languages. It's less about being a deep specialist in just one syntax and more about understanding the trade-offs and being able to learn quickly, especially with AI assistance.
And even databases are changing, right? Not just the old relational model.
Definitely. We're seeing a huge rise in NoSQL databases. Things like graph databases, perfect for modeling relationships in social networks or recommendation engines, document databases, key value stores, and also NewSQL databases that try to offer the scalability of NoSQL while retaining some of the consistency guarantees of traditional relational databases. The whole landscape is diversifying.
All this evolution,
Yeah.
the languages, the paradigms, the databases, the rise of AI,
Yeah.
it really sets the stage for this next big leap you mentioned earlier, Software 3.0.
Exactly. All these threads converge, leading to a fundamental transformation in how software itself is conceived and built.
Okay, let's jump into that cognitive revolution. We laid the groundwork, software engineering, the incredible diversity of programming languages. Now let's get into these truly transformative eras of software development, where AI stops being just a tool and becomes, well, a partner.
A creative partner, exactly. We can generally think about software development evolving through three distinct eras. Each represents a major paradigm shift.
3 eras.
Yeah.
Okay, what's the first one?
Software 1.0, the classical stack, human-authored. This is the traditional way how we've mostly built software for decades.
The way we just discussed, humans writing code line by line.
Precisely. Meticulously crafting every single line in languages like C++, Python, Java, JavaScript, using text editors or IDEs. Humans are the sole authors, defining every logical step, every variable, every function.
And this is still dominant for many things.
Oh, absolutely. It remains the main way we build regular applications, websites, mobile apps, big enterprise systems, microservices, anywhere you need explicit human control and really fine-grained deterministic logic. The code is a direct expression of human intent.
Okay, Software 1.0, the familiar world. What's Software 2.0?
Software 2.0, the data revolution, machine learned. This term was really popularized by Andrej Karpathy, and it marked a radical departure.
How so? What changed?
Here, the software isn't written by humans typing explicit code. Instead, it's effectively written by optimization algorithms training neural networks on massive datasets.
Wait, the code is the trained network.
Essentially, yes. The program becomes the learned weights and biases within the neural network. The focus shifts entirely to statistical computing, deep learning, ML algorithms. This was the big boom of data science.
So humans weren't coding logic, they were curating data, designing network architectures.
Exactly. Data itself effectively became the program. Think image recognition systems, machine translation models. These aren't built with explicit if-then rules. They learn patterns from data as Software 2.0.
Okay, a very different way of creating intelligence. So what's Software 3.0 then? This is the now.
Software 3.0, the cognitive AI revolution. AI as creative partner. Yes, this is the era Karpathy identifies as the now, and it's another huge shift. Here, AI transitions from being just a component inside an application, like a recommendation engine,
Right.
to becoming an active creative partner in the development of the application itself.
So AI helps build the software.
Correct. The core idea driving this is natural language programming. NLP, NLU, NLG. You communicate with the computer using human language.
Like we talked about with prompt engineering.
Exactly. Specifically, using context-sensitive prompting, which is sometimes called context engineering. It's not just telling the AI what to do, but giving it enough background, constraints, examples, maybe access to documentation or existing code so it can deeply understand your intent.
And then the AI generates the code.
Yes. The AI, whether it's a big generative AI model or a more specialized agentic AI, then generates the actual source code needed.
And that code could be.
It could be traditional software 1.0 code Java, Python for a web app, C++ for a system component, or it could even generate software 2.0 code Python or R scripts designed to train a new machine learning model.
Wow. So AI is writing both traditional code and the code for AI models.
Potentially, yes.
Yeah.
And this can be human co-piloted, where the AI is like an incredibly powerful assistant, suggesting code, completing functions, finding bugs.
Like a pair programmer on steroids.
Kind of. Or, in increasingly sophisticated scenarios, it could become fully autonomous for certain tasks, generating entire modules or features based on high-level requirements. It's like AI is becoming the new architect, or at least a powerful co-pilot handling a massive amount of the implementation detail.
Okay, that leads directly to this concept you mentioned, vibe coding. It's a great name. What exactly is it? How does it work in practice?
Vibe coding is really the emerging pattern of code generation that defines Software 3.0. It's where machines play the major role in actually creating the code based on these natural language prompts, and humans primarily assist, guide, refine, and validate.
Human-assisted, machine-generated code.
That's the perfect definition. The vibe part refers to the AI capturing the intent, the context, the underlying goal or feeling behind the human request, not just the literal words. It allows the AI to generate code that hopefully matches that deeper conceptual understanding.
And there are tools enabling this now.
Yes, absolutely. Tools like Replic's Ghostwriter or Cursor, which is an AI-first code editor, and others like Windsurf. They're at the forefront of enabling this new workflow. The developer's primary input shifts from typing every character to articulating high-level requirements and then steering, debugging, and integrating the AI's output.
So if AI is doing so much of the heavy lifting, automating huge chunks of the development lifecycle, what are the really big transformative shifts we're seeing because of Software 3.0? What does this unlock?
The implications are profound, honestly. They touch everything from who can create software to how quickly we can innovate.
Okay, like what? Give me the big ones.
First, democratization of coding. This is huge.
Meaning more people can do it.
Exactly. Non-programmers can now potentially build software just by providing prompts in plain English. This massively expands the pool of creators way beyond traditionally trained software engineers.
So domain experts, designers,
Yeah.
they could generate code.
Yes. Imagine a domain expert in biology describing an experiment, and an AI helps generate the Python code to analyze the data. Or a designer describing a user interface, and the AI generates the initial HTML and CSS. Business analysts, sales professionals. Suddenly, they're empowered to prototype or even build tools without needing years of coding experience.
That could really change things. Addressing the talent shortage, maybe.
It directly addresses that chronic mismatch between the huge demand for software and the limited supply of traditional developers. It distributes creation capabilities more broadly.
Okay, democratization. What else?
Accelerated development velocity. This is almost a given.
Faster development.
Much faster. Automating the generation of both Software 1.0 code and Software 2.0 models significantly speeds up the entire SDLC. Things that used to take months of manual coding can now potentially be prototyped or even implemented in weeks, maybe days for simpler things.
So faster time to market.
Yeah.
Lower costs.
Definitely faster time to market for new products and features, and potentially a substantial reduction in the total cost of ownership, TCO, for companies. We're seeing real evidence of this. Think about Cognizant, a major IT services company, stating their aim to generate 50% of their code using AI within just a year.
50%. That's staggering.
It's an unprecedented shift in efficiency if they achieve it. Shows how seriously this is being taken at scale.
Okay, speed and accessibility. What else?
A paradigm shift in abstraction for developers themselves.
Meaning they work at a higher level.
Yes. They can shift focus away from the nitty-gritty syntax details, the commas, semicolons, exact function names in language X versus Y towards higher-level concerns. Problem decomposition, overall system architecture, design patterns, user experience.
So less coder, more designer or architect.
Exactly. They become more like system designers, orchestrators of AI capabilities, critical thinkers. They leverage AI as a powerful tool, moving their own value up the abstraction stack.
Interesting. Any other benefits?
Enhanced explainability and interpretability, potentially.
Really? I thought AI was often a black box.
Well, for Software 2.0, the deep learning models, yes, interpreting the weights can be very hard. But when AI generates Software 1.0 code, like Python or Java business logic, that code is often human-readable. It looks like code a human might have written.
Ah, okay. So it's easier to understand than a neural net.
Often, yes. This can make debugging, understanding, and maintaining the AI-generated code potentially easier than debugging the internal state of a complex learned model.
That's a counterintuitive benefit. What else?
Increased adaptability for developers. It becomes much easier and faster for humans to learn new capabilities or move into new programming domains.
Why?
Because they don't necessarily need to master complex new syntaxes from scratch. The AI can bridge that knowledge gap, translating their intent into the target language. This allows for more fluid transitions between technologies.
And maybe even self-evolving systems.
That's the longer-term vision, yes. With agentic AI, you could have systems that iteratively improve their own prompts, refine their own code based on feedback loops or performance monitoring, leading towards self-optimizing, maybe even self-managing systems that adapt over time with less human intervention.
This sounds like a productivity dream. Truly transformative. But every revolution brings new challenges, new complexities, right?
Absolutely. It's never that simple.
How does Software 3.0 actually reshape the underlying architecture? What are the new building blocks, the new pillars? Is it a total overhaul, or does it build on what we had?
That's a crucial question. A Software 3.0 fundamentally reconfigures the architectural paradigm. It introduces entirely new foundational layers while also leveraging and transforming existing concepts.
Okay, so what are these new pillars?
One major shift, LLMs as the new operating system.
Large language models.
Yeah.
As the OS.
Yeah.
How does that work?
Think of the LLM as becoming the central backbone, the orchestrator for intelligent applications. It's not managing hardware directly like Windows or Linux, but it's managing the flow of information and intelligence.
Oh.
It aggregates context-sensitive data from all sorts of systems, upstream databases, downstream APIs, user interactions. It uses technologies like retrieval augmented generation, RAG.
Gradually.
RAG allows the LM to pull in external, factual, up-to-date information from knowledge bases or documents before generating a response or code. This grounds the AI, makes it more accurate, reduces hallucinations.
So it looks things up before it answers.
Kind of, yes, to ensure its knowledge is current and relevant. LLMs also coordinate interactions, potentially using agent-to-agent A2A protocols, allowing different specialized AI agents to communicate and collaborate on complex tasks. Everything starts to revolve around the LLM orchestrating these intelligent interactions.
Okay, LLMs as the core. What else?
AI agents, the new unit of abstraction. These are the active components.
We talked about these descendants of OOP objects, but smarter.
Much smarter, much more autonomous. Unlike a passive OOP object waiting to be called, an AI agent is capable of acting, knowing, accessing knowledge, planning, and implementing decisions on its own to achieve goals.
So they can reason and act independently.
Within their defined scope, yes. In many specific use cases, these agents can already compete with and sometimes outperform human intelligence for tasks like data analysis, complex scheduling, code reviews, customer service interactions, even managing simple business processes. They are the intelligent workers in the Software 3.0 architecture.
Wow. Okay, LLMs orchestrating, agents acting. What else holds it together?
Knowledge graphs and RAG, the cognitive foundation. This is where the understanding comes from.
Knowledge graphs, like interconnected data.
Exactly. Structured repositories of facts, entities, and their relationships. Think of it like a highly organized brain for the AI. They connect real-time information and provide rich context for the AI's reasoning. Coupled with RAG, this allows AI systems to move beyond just pattern matching towards genuine understanding, enabling large concept models and large reasoning models.
They provide the memory and the context.
Precisely. They form the cognitive underpinning for the AI agents and the LLM.
Okay, so LLMs, agents, knowledge graphs. It feels like a shift from just storing data to reasoning about it.
That's the cognitive thread. It represents this profound evolution from traditional systems of record, our databases that just store stuff, to true systems of reasoning, where intelligence, inference, and autonomous decision-making are core capabilities. Software isn't just processing data anymore, it's understanding, interpreting, generating insights, taking action.
And how do we interact with all this?
That's the human-agent interface. Our interaction with technology becomes fundamentally different. More intelligent, less like talking to a dumb interface.
Less clicking menus, more conversation.
Potentially, yes. Instead of navigating complex menus or remembering specific commands or syntax, we'll increasingly communicate with systems that understand our intent more deeply, maybe anticipate our needs, take proactive actions based on sophisticated reasoning. It's a more natural, collaborative interaction model.
It sounds incredibly powerful. But as you said, every revolution has its challenges, its risks. This can't all be smooth sailing.
Not at all. There are significant hurdles and potential downsides we need to grapple with.
Okay, let's talk about those. You mentioned a double-edged sword for developers earlier.
Yes. On one hand, it's amazing. AI handles the tedious, routine coding, freeing developers to focus on higher level, more creative, more strategic problem-solving and architecture. That's incredibly appealing.
Makes them cooler or lazier, maybe, in a good way?
You could say that. But the flip side is the risk of overdependence. If developers rely too heavily on AI for basic coding, will foundational skills atrophy? Could we see a loss of individual specialization and deep understanding?
And debugging. You mentioned that could be harder.
That's a major operational challenge already surfacing. While the AI might generate code incredibly fast, thousands of lines in seconds, understanding why it generated that specific logic, especially for complex or non-standard problems, can be really opaque.
So faster initial coding, but potentially much longer testing and fixing.
It's a real risk. Debugging complex, raw AI-generated code can be significantly harder than debugging human-written code you understand intimately. The time saved up front could potentially be lost or even exceeded in the validation and fixing phase. It's like being handed a brilliant but sometimes very eccentric solution. It might work, but figuring out how or why can be tough.
And then there are the more dramatic risks, like that anecdote you confirmed about the Replit tool accidentally deleting a customer's database.
Yeah.
That highlights the AI going rogue fear, doesn't it?
It absolutely does. It's a stark, real-world reminder of the inherent risks in giving too much autonomy or uncontrolled power to these still nascent AI systems, especially code generation tools that can have profound system-level effects.
So mistakes can be amplified massively.
Potentially, yes. That incident underscores the critical need for extremely careful oversight, robust testing, fail-safes, and keeping humans firmly in the loop for validation before AI-generated code, especially code that modifies data or infrastructure, gets anywhere near production. The pain of these kinds of incidents is already being felt, driving home the need for caution.
Okay, beyond the technical and operational risks for developers and companies, what about the broader societal debates? This must be stirring up some big questions.
Huge questions, absolutely. The discussions are complex, multifaceted, and really just beginning.
Like jobs, employment security for software engineers.
That's the major one, yes. When a company like Cognizant publicly targets generating 50% of its code with AI, it naturally fuels the debate about AI replacing human jobs in software engineering.
So are the robots taking the coding jobs?
It's complicated. The dominant view isn't necessarily outright replacement, but a significant shift in the nature of the work. It really emphasizes the survival of the fittest through adaptability.
Meaning developers need to adapt or risk becoming obsolete.
Essentially, yes. The reality is likely that the type of jobs will change. Routine coding tasks might become heavily automated, but new roles will emerge: prompt engineers, AI trainers, system orchestrators, AI ethicists, people who manage and validate AI output. Those who embrace these tools, learn to leverage AI, and move up the value chain to focus on architecture, strategy, and overseeing AI systems will likely thrive. Those who resist adapting their skill set may find traditional coding roles less in demand over time. It's about upskilling and reskilling into these new, higher-value roles.
Okay, so a transformation of roles, not necessarily mass unemployment, but requiring adaptation. What about ethics? Autonomous AI making decisions.
This is perhaps the most critical area for society. As AI systems become more autonomous and start making decisions that can have real-world impacts in finance, healthcare, transportation, justice, the ethical considerations become paramount.
How do we ensure they make good decisions?
That's the multi-trillion-dollar question. It necessitates the urgent development of robust constitutional AI frameworks, designing AI systems with built-in ethical guardrails, principles, and values from the ground up. How do we ensure fairness, transparency, accountability, and prevent bias in autonomous systems? These are massive challenges.
And control, vendor lock-in.
Also big concerns. As Software 3.0 likely relies heavily on large models and platforms from major cloud and AI providers like Google, Microsoft, OpenAI, and Anthropic, there are valid worries about vendor lock-in, data privacy, and the concentration of power. And underpinning all of this is the critical need for effective regulatory governance and shared ethical standards in AI development globally. We need rules of the road to ensure these powerful technologies are developed and deployed responsibly.
Designing responsible AI feels like one of the defining challenges of our time.
It truly is.
So if this complex, challenging, but powerful Software 3.0 is the now, what's on the horizon? What does the road to Software 4.0 look like? Are people already thinking that far ahead?
Oh, absolutely. Experts and researchers are actively projecting the next phases. Building on the trajectory of Software 3.0, the roadmap gets increasingly ambitious.
Okay, give us a glimpse. What's the near-term future look like, say, the next 3 by 5 years?
In the near term, roughly 2025, 2028, the focus will likely be on really mastering Software 3.0. We'll see widespread adoption of AI code generation, maybe reaching that 80% assisted generated code figure in many places. This era is being called the agentic orchestration era.
Agentic orchestration?
Yeah.
Meaning managing the agents.
Exactly. We'll see the rise of a whole new discipline, agentops. Similar to DevOps for code, agentops will focus on the unique challenges of managing, monitoring, governing, and securing the behavior of these increasingly complex and autonomous AI agents. Security itself will evolve too, with DevSecOps maturing into DevSecOps 3.0, deeply embedding zero-trust security principles right into the AI-driven CI/CD pipelines from the start.
Okay, mastering agents. What about the midterm, say 2028, 2032?
The midterm, 2028-2032, could see the rise of autonomous meta companies.
Meta companies, what are those?
As agentic orchestration matures, and AI gets even more capable, the idea of fully autonomous software companies could move from science fiction towards reality. Imagine AI systems, meta companies, that can autonomously design, clone, deploy, operate, and even manage other software businesses, dynamically adapting to market conditions with minimal human oversight.
Wow. An AI running a software company that builds software.
That's the concept. In this era, human developer roles would ascend even higher. They'd focus almost exclusively on setting high-level strategic goals, designing the ethical frameworks and constraints for these autonomous entities, conceptualizing grand system architectures, and managing the cognitive debt.
Cognitive debt, like technical debt, but for AI understanding.
Exactly. The intellectual burden of overseeing, understanding, and maintaining systems so complex, so intelligent, potentially self-modifying, that no single human fully grasps all their inner workings. We'll also likely see accelerating cyber-physical fusion AI orchestrating complex real-world systems like smart cities via digital twins, and maybe the first impacts of quantum machine learning potentially breaking current cryptographic standards.
That's a radically different world. What about the long term, 2033 and beyond? Is that software 4.0?
That's when many experts predict the true dawn of software 4.0, roughly 2033, 2035. What might that look like?
Yeah.
We could see large-scale, decentralized autonomous systems managing critical infrastructure energy grids, global supply chains, transportation networks, leveraging ubiquitous edge computing to make decisions locally and instantly.
AI running the grid.
Potentially, with human oversight frameworks, of course. We might also see fully autonomous R&D, where AI acts like scientists, designing novel algorithms, discovering new materials, maybe even generating entirely new programming paradigms or languages optimized for AI collaboration. And even regulatory AIs might emerge, AI systems designed specifically to audit other AIs for ethical compliance and adherence to societal norms.
AI auditing AI. Okay, that leads to the ultimate frontier you hinted at, cognitive programming. That sounded like pure sci-fi.
It is highly speculative, of course, but it's the direction some are pointing towards. We're talking direct brain-computer interfaces, BCIs, for coding. Think Neuralink-style technology.
So coding, with your thoughts.
Potentially, where your intentions, your mental models, your abstract ideas about a program could be translated directly into executable code, perhaps bypassing traditional programming languages altogether.
Think the code into existence.
That's the ultimate vision. It represents a fundamental blurring of the line between human cognition and machine execution, a step towards digital singularity, maybe transhumanism, where the way we create and interact with software becomes completely intertwined with our own thought processes. Some experts believe elements of this might happen sooner than we think, profoundly altering what it means to be a creator in the digital age.
Wow. Okay, that is a lot to process.
Yeah.
We've journeyed from the absolute basics, what software even is, through the intricate, evolving world of programming languages, all the way to this revolutionary landscape of software 3.0, vibe coding, and even glimpses of software 4.0 and cognitive programming.
It's a massive arc.
We've really seen how AI is shifting from just being a tool within software to becoming an active creative partner in building software, moving from meticulously human-authored lines of code towards this new era of machine-generated artistry, guided by human intent. It's truly a seismic shift.
It really is changing the bedrock of how we build our digital world. And our goal throughout this deep dive, especially focusing on those languages and the software 3.0 paradigm, was to give you that shortcut, that distillation.
Provide those aha moments.
Exactly, transforming all that raw information out there into some genuine insight you can use.
So here's a final thought for you, our listener, to mull over. As AI continues this trajectory, becoming an active creative partner, enabling even non-programmers to build complex systems, what new skills will you need to cultivate? How will you adapt to navigate and thrive in this rapidly evolving digital landscape?
Yeah, consider how your own role, whatever it is, might transform in relation to creation and problem solving. How might you need to operate at a higher level of abstraction, collaborating with these new intelligent tools?
It's a fascinating question for all of us. The conversation around software's future is clearly just beginning.
It's a dynamic, exciting, and maybe slightly daunting space to watch. It truly marks a new era in human-computer collaboration.
Thanks for diving deep with us today. We'll catch you on the next one.